Hello, and welcome to Lecture 9 on the topic of the normal force, where we're going to be covering section 4.3 from Survey 11th edition. Okay, so this is a single topic lecture. We're just going to introduce some key terms and do some examples that apply to the normal force. Okay, so let's get the key terms out of the way. All right, we can see the normal force is one of them, as well as gravitational force. I want to make sure we understand the difference between them. So the gravitational force is the pull of gravity towards Earth. Okay? Now, it could be other planets, but for our intents and purposes, we'll think of it as Earth. A force that is proportional to mass of an object and gravitational acceleration. So if either mass go up or gravitational acceleration go up, then so too will the gravitational force. So it's a direct proportionality with those two variables. Okay? That said, gravitational acceleration is assumed to be constant on the surface of Earth. Okay? But if it did change, then so would gravitational force. It always points towards the center of Earth. Since most of our problems involve small things, especially in this chapter, it basically points down. But if we were to take into account the curvature of Earth, or we're talking about satellites, for example, then it would be better to think of it as pointing towards the center. In fact, it always points to the center, but when you're in a flat room, it effectively points down. The gravitational force points down. And lastly, it is created by a law that all mass attracts all other mass, a law that we won't define until a later chapter. Okay? All right, so then what is the difference between weight and mass? Well, weight is just gravitational force. Those are synonyms, right? Interchangeable terms. Mass is a measure of all the matter in an object, and weight is, well, it's a force, right? One has units of kilograms, the other has units of newtons, okay? Now, weight is not the same as the normal force, okay? The normal force is a reaction force from floors, simply put, right? And I try to kind of put the first expression as the easiest way to remember a definition, all right? Maybe not the most technical, but the easiest, most applicable. So, in that sense, weight is the action force. The normal force is the reaction force. Weight is the force on the floor by an object. The normal force is the weight, or is the force on the object by the floor. Okay, so the normal force is the force that points perpendicular to a surface and is equal in magnitude to the force pushing on that surface. So it need not always be weight that is the force pushing on the surface. It could be some other external force, okay? But if you push on a surface, that surface pushes back, and we call that the normal force. By the way, the term normal here doesn't mean normal in the sense of ordinary. It actually means perpendicular. So normal is a mathematical term that means perpendicular at 90 degrees to a surface. Okay? All right, let's look at our key formulas. Not too much going on here. We could perhaps skip key formulas, but there's a couple I think that are good to think about. All right, so let's identify them. Oh, I forgot. The normal force is also called the support force. That's another common term you see for it. In this class, I think it's less common to call it the support force, but in other physics classes, certainly it is called that. All right, so both the formulas I have here only apply to level ground. So that means there's a couple of examples I'm going to do where we couldn't apply these problems as written, but we'll mention that when we get there. All right, this first line here has a stipulation. It says this formula is true if acceleration equals 0. So that says that the floor is not accelerating. That's the idea. If the acceleration equals 0, that means the floor is at rest or is moving at constant velocity. It just can't be accelerating. All right. The normal force here is identified as a vector force with a subscript of n. Okay, that's the way we write the normal force. Okay. Lastly, we've got the gravitational force, another vector, subscript of g. All right, so what I'm saying here is that the gravitational force is equal to mg, and whatever direction the gravitational force points, the normal force points in the opposite direction as indicated by the negative sign there, right? Because you multiply a vector by a negative sign, that's like flipping it 180 degrees. Well, what's going on in the next line? So the next line just says that this is when the floor is accelerating, like an elevator, right? So when your floor is moving, specifically when it's accelerating, it doesn't matter if it's moving at constant velocity, but if it's accelerating, then your formula changes. Because now, your sum of forces, according to Newton's second law, is not equal to 0, which means that Fg does no longer equal negative Fn. Instead, the difference between Fn and mg is equal to ma. And I'm just getting this just from rewriting Fnet equals ma. This is so Fnet is right here, and of course ma is just on the right-hand side of the equation as written, okay? And that's a big thing we're going to get used to. We're going to do this a lot throughout this lecture and then the next 2 lectures for this chapter, is write the net force as multiple forces in scalar form. Okay, here this is a vector equation, but if I wanted to solve something, I need to split it into components if necessary. Okay, so we have 3 types of problems in this particular lecture. We have type 1 problems that involve the normal force as measured on other planets where gravitational acceleration differs from Earth's. Okay, so that's a common enough type of problem that I included it as one of the 3 types. Type 2, problems that involve the normal force in accelerating non-inertial, right, that's a term we introduced a few chapters back, reference frames like elevators. Okay, so that's where the floor is accelerating. And finally, type 3, problems that involve the normal force exerted by non-level surfaces like ramps. And we're going to do a lot with non-level surfaces, especially in the lecture on 2-body problems. All right, so this is definitely a kind of a precursor of things to come and a good chance to sort of see what a ramp looks like, how to deal with forces and force diagrams when there are ramps. All right, but first, let's look at type 1 and type 2. Problems, that is, or examples. All right, so let's get into our practice. Example 1. A net external force of 7.5 newtons acts on an object that weighs 22 newtons on Earth. What is the acceleration such a net force would generate on Earth, and what is the acceleration such a net force would generate on the Moon? Okay, so let's look at part A. This is a problem that we could have seen in the last lecture. We're just going to use Newton's second law, Fnet equals ma, in scalar form. Solve for A, right, which is just going to be the net force that we were given, divided by m, okay? In this case, I'm going to find m by taking the Earth weight and dividing it by Earth acceleration. Excuse me. And so then that gives me an acceleration of 3.34 meters per second squared. All right? So that's, if I applied a net force on an object, and you can think of this net force in any direction, but I think it's helpful maybe to think of this net force as pushing something across like a smooth surface, like an air hockey table or an icy lake, right? I'm just applying a force for some amount of time, right? It doesn't matter, but I am applying a force, and I'm just curious about what acceleration is going to be created while I apply that constant force. That's it. That's the question. Okay? So what happens if I do it on the Moon? All right? And by the way, when I do take the weight of the object on Earth and divide by gravity, I find that its mass is 2.24 kilograms. So basically, you could have thought of that as a preliminary step. Based on this value, you can just find the mass and then kind of set that value aside and that's something you can use in future parts of the problem or subsequent parts of the problem. Okay, so what about on the Moon? Well, on the Moon, we're just going to take Fnet and divide by m. Right? Well, what if I had taken the 7.5 newtons? Well, if I had taken the 7.5 newtons, the weight of the object on the Moon, I wouldn't have divided by 9.8, would I? I would have divided by 1/6 of 9.8. If I'd done that, I would have got 2.24. Okay, well, I guess, yeah, mass doesn't change, right? Mass is independent of where you are. Mass is universal, truly. On any planet, any world, any corner of the universe, mass is the same. Okay? So 3.34 meters per second squared again. Well, why is that, right? Well, because neither net force nor mass are dependent on gravity, right? Net force might take into account gravity, but it's not dependent on gravity, right? That's the difference. Okay, well, what would be different between the Earth and the Moon? Because obviously, things are different. I mean, we've seen videos of astronauts walking on the Moon. The 1/6 gravity has a real effect on physics, including forces. So what is that, right? How do we see that in practice? Well, in part C, we're asked if this force was applied for 1 second, and this force being the one that we mentioned before, right? So the net force of 7.5 newtons. Okay. So if that force was applied in both situations. Oh, by the way, this was not the weight on the Moon. This is the external net force. A moment ago, I misspoke. So I want to be clear on that. This is the external net force that's applied on either Earth or the Moon. This was not the Moon weight. Okay. So find the initial velocity for v0 equals at. So we'll take the 3.34 meters per second squared that we found was independent of where we were, multiplied by the 1 second to get our final velocity. And this is just using kinematics. Okay? So then we're going to use the range formula for level ground because we're asked, about a projectile that was angled at 45 degrees above, above the horizontal, right? And then it's shot a certain distance. How far does it go? Okay? Well, all right, so what is going to be different now? Well, look, now the gravitational acceleration of the Earth shows up in the problem. Likewise, the gravitational acceleration of the Moon shows up in the problem. Before it didn't, really, right? The mass just showed up, right? It was kind of deceptive that the weight showed up because we just divided by g, right? So in a very real sense, this problem was independent of gravitational force. This one is not independent of gravitational acceleration. So the kinematics change, all right? So again, we applied a certain force, got a certain final velocity that was a launch velocity, all right? And then we find out that the range on Earth is 1.14 meters, but the range on the Moon, where gravity is 1/6 as much, is significantly further. It's 6.83 meters. All right, so then the difference between the ranges is 5.69 meters. Right, so a very, very significant difference between the ranges because things weigh less on the Moon. It is easier to launch things on the Moon. They don't fall as fast. Okay? The gravitational pull on objects on the Moon is not as great as on objects on Earth. All right, example 2. On a distant world orbiting another star, an alien drops a rock from rest off the edge of a cliff that is 505 meters tall. The alien observes that the rock takes 12 seconds to fall. If this rock has a mass of 6.09 kilograms, then what is the weight of the rock on this world as a percentage of the weight of the same rock on Earth? Okay, so I'm going to use kinematics to find acceleration. So start with kinematics just like in the last example. Okay, this would be the appropriate equation based on the fact that I was given a height and a time. Okay, so then I'm going to go ahead and solve for a because that's my unknown. And it turns out that my gravitational acceleration on this particular world, I forgot my negative, is negative 7.01 meters per second squared. It's negative because it's in the opposite direction of assuming that the height is positive. Right? So I'm measuring positive y is up, thus gravity must be a negative vector. Okay, and you can see the negative showed up here, but I did not include it in my final answer. My mistake. All right, so then I want to find the force of gravity. Okay, so I go ahead and find the force of gravity. Here I'm going to take the mass of the object because I was given it, and find out then that the gravitational force on this particular object, on this particular world, is 42.7 newtons. Now here's the thing. In this problem, I was actually asked for the weight of the rock as a percentage of the weight on Earth. And so I actually could have left this information out. I didn't have to give you the kilograms because we're looking at a ratio, and the kilograms are going to cancel out. But since we were given it, I figured I might as well solve for it and get a number just so we can see some practice here. Okay, so then I'm just going to take the gravitational force on the alien world divided by the gravitational force on Earth and multiply it by 100. This will then give me the percent of the weight on the alien world as compared to Earth. Okay, plug in our numbers. Right here in the denominator, this is just going to be the gravitational force on the object on Earth. In other words, its weight. We can see it's going to be significantly bigger. It's going to be closer to 60 newtons as opposed to 42.7 because gravitational acceleration on Earth is bigger than 7, right? It's 9.8. So then we get 71.6%. But you know what? We could have got that same 71.6% by just taking 7.01 dividing by 9.8 and multiplying by 100. All right? Let's do a concept question. And I like this one. All right? I ask this in all my physics classes, including my descriptive physics classes. And it does actually throw people off. And so you might be surprised with the result yourself. There are two common types of scales used to weigh people. Okay? By far the most common is spring scales, think of a typical bathroom scale, and they've been digitized, but in some sense they have some sort of compressible material, maybe like a particular plastic that changes its resistivity based when it's compressed, but it's still effectively a spring-like material. And so you compress it, it gives you a reading, and there you go. Okay? So that's a spring scale. On the other hand, there's also counterweight scales. This would be like your triple beam scale in a laboratory. This is the old scales that you would see in doctors' offices where they slide the big metal sliders that clip into different numbers as they slide across. Right? Those are all counterweight scales. All right? Definitely a different mechanism. No spring involved. Just a balancing. Okay? So if you took both types of scales to the moon, all right, real waste of money, right? Would they both still give the same weight as on Earth? Okay? No, they wouldn't. Okay? But not both of them? One of them would agree, the other wouldn't. Let's see. So the spring scale would read less because of your decreased gravitational force on the moon. You weigh less, thus the normal force exerted by the spring is less. Less normal force by the spring means less compression. We'll talk about that when we talk about Hooke's law and spring forces. But for now, I think it hopefully makes sense, seems very believable that, and at the very least, regardless of whether the spring is compressed or less or not, just the very understanding of a spring scale is just going to read less, okay? Because you're pushing on it less, thus it's pushing back less with the reaction force. But what about the counterweight scale? Well, the counterweight scale would actually read the same as on Earth. It would totally agree. Because the counterweight scale is measuring mass. So whatever reading it had on Earth will be the same as the reading on the moon, okay? Whereas the spring scale is a measurement of force. Thus it is affected by whatever is the ambient gravitational pull, all right? And the explanation here is because both you and the counterweights would have equally decreased gravitational force, but you'd still have the same relative masses, thus it would still give the same reading, all right? So is the counterweight scale better? Well, it depends, right? Okay, so now let's do some examples of accelerating floors, okay? We'll start with one where there's actually no acceleration in example 2, just to kind of set the stage for example 3. So you stand in the elevator moving at a constant velocity, all right, of 2 meters per second. That number is completely unnecessary. We don't care how fast the elevator is moving as long as it's moving at constant velocity. Also, we don't care if it's moving upward or downwards because constant velocity, okay? You are holding a heavy bag by a single strap. You have a mass of 70 kilograms and the bag has a mass of 12 kilograms. What force does the bag exert on its strap? What is the net force on the bag strap? What is the normal force exerted by the floor of the elevator on your feet? Okay, let's see. Here's the picture. All right, here's the elevator. Here is gravitational acceleration, okay, external acceleration, but the elevator doesn't have its own acceleration. All right, so we have 3 objects and we'll draw forces acting on each. All right, these are introducing the idea of force diagrams, which we kind of saw in the last lecture. We're going to see a lot more of them. These are also called free body diagrams, okay, because I guess the body is free to move depending on the forces, right? All right, so on the bag, there's a force pointing up and a force pointing down. The gravitational force points up. The force pointing up, we'll call it the tension force, although we won't formally introduce the tension force until the next lecture. But for now, sure, let's call it a tension force. It's a force that's supporting the bag, okay? Some sort of support force, okay? So then the net force on the bag is the upward tension force minus the downward gravitational force, and that equals ma. But a is 0 because the elevator has constant velocity, all right? So that means that the tension force is equals the gravitational force, as we can see here, by setting them both equal to 0, moving it over. So then the tension force must be equal to 12 kilograms times 9.8, all right? And we were asked for what force does the bag exert on its strap. Well, the force that the bag exerts on the strap, zoom in a bit on this, is none other than the tension force. So there we go, 118 newtons. Okay, that's how much the bag pulls on its own strap. Okay, meanwhile, the strap, okay? Now this is an idea I presented before. The strap we're going to see has 0 net force acting on it. Not because it's not because it's not necessarily accelerating, but because the strap, like ropes and strings and all of our problems, is assumed to be massless. By definition, the tension acts on both ends of the object under tension. Okay? And here's the thing, the net force is tension minus tension, but it's equal to 0. But why is it equal to 0? It's equal to 0 because of no mass, not because these two forces necessarily cancel out. In fact, the only reason that these two forces are equal to each other is because of the no mass. Okay? So potentially, right? In this case, since the acceleration is 0, the left-hand side of the equation of F net equals ma would have been 0 anyway. But the thing is that the net force on the strap will always be 0. And I'm going to show you that again in the next example. Okay? But let's move on to the more important part C. All right? So now let's look at all the forces acting on the person. There are 3 forces because the strap that was getting pulled on by the bag is then also pulling on the person. And that's again because massless straps, massless ropes, massless strings, they're perfect transmitters of force. So that force on the top then must have, by Newton's third law, an equal opposite force of the hand pulling on the rope. Okay? Well, actually, this is the hand pulling on the rope, and this is the rope pulling on the hand. Okay? And the hand is part of the body. We're treating the body as one solid object. Meanwhile, there's a gravitational pull on the person, on you, 70 kilograms, and the normal force because you push on the floor pushes back. All right? So then our F net is 3 separate forces equal to ma, but again, A is 0, so that means that the normal force minus the tension force minus the gravitational force is just equal to 0, which means that the normal force is just the sum of the tension force plus the gravitational force. We know that the tension force is just m bag times g from part A, and then we know that the gravitational force is just m person times g by the definition of the gravitational force. And so we plug in our numbers, 118 newtons plus 70 times 9.8, right, which is going to be around 700. So our final answer is 804 newtons. Okay, that if you were standing on a scale that gave you a reading in newtons, it would read 804. All right, but what if the elevator is accelerating? So you stand in the elevator slowing down at a rate of 2.8 meters per second squared as it moves upward. Okay, so if you're moving upward and the elevator is slowing down, okay, so that means you have an upward velocity, but the acceleration is causing that velocity to decrease in magnitude. What direction must the acceleration face? Think about it, okay? Down. So we see then that now our situation still has the external gravitational acceleration, but now there's also a acceleration of the reference frame that is down as well, okay? And that again is because you're moving upwards but slowing, okay? And we'll summarize all those cases in just a minute in the next concept question. All right, so it's going to be all the same process here. It's going to basically be all the same force diagrams, all the same application of Newton's second law in terms of the F net equals ma. The only difference is that each and every time where we have an equals ma, the a will not be 0 anymore, which obviously will change the results. But we know what the a is. It's just 2.8. So we will just be able to plug in the number. It won't be a big complication, but it definitely will change the results. All right, so start on the bag. There is our force diagram on the bag. All right, so F net is just tension minus gravity equals m bag times a. All right, so now the tension is the sum of m bag times g plus m bag times a. Why do we know that? Okay, well, let's think about it, right? So we've got, but let's, because all I did is just move gravitational force over here. That's why, simply put, right? And gravitational force, by definition, is just m bag times g. But here's the thing. Now, when I plug in the numerical value of a, I have to acknowledge that it's negative. So notice here there's a positive, so I'm adding a negative number, hence the negative 2.8. Okay, so that means now that my tension force, essentially the weight of the bag that the hand is experiencing, is less than when the elevator was moving at constant velocity. And constant velocity might as well have been rest, remember, right? So why does the bag weigh less? The bag weighs less because the acceleration of the reference frame, the acceleration of the gravity is down. All right, and this makes sense. Think about an elevator. As you're going up in an elevator, approaching a top floor, and the elevator starts to slow in approach to that floor, you feel a little bit lighter, okay? It's the opposite of when you're on the ground floor in the lobby and you get an elevator, and the elevator just starts on its ascent. That first moment of starting up, you feel heavier for a moment, okay? So this is the lighter case, all right? So we should expect all the values to be less than they were in the previous example. All right, let's go ahead and look at part B. Well, what's going to happen in part B? Now there's non-zero acceleration, but, okay, now what makes the right-hand side of the equation 0 is the massive strap. Before they were both 0, so it was kind of a duplicate of zeros. But here we got the massive strap, which gives us the same case that the net force on the strap is 0. Okay, even though it's accelerating, and that's only possible because it has 0 mass. Okay, now is that real? No, it's an approximation, but a good one. All right, now finally the person. On the person, we've got a very similar situation. Net force, there's 3 forces, but they're going to be equal to a non-zero ma. All right, I'm going to work that out, solving for the normal force, moving everything that isn't the normal force over to the right-hand side of the equation. All right, and then I'm going to plug in my values, right? I already know the tension force, so I'm just going to carry that over from part A. And then for Fg plus m person times A, I'll just plug in for Fg, m person times g. All right, and then of course this A is going to pick up a negative, and we can see that right there, right? Because I'm adding a negative number, and I factored out the 70 because there is a like term on those two. And so then my final value is 574. Okay, so if I was standing on a scale when the elevator was moving at constant velocity, it read 804. But when the elevator is accelerating downwards, it now reads 574 newtons. Okay? And newtons are kilogram meters per second squared. All right, let's do a quick concept question here. Okay, so let's consider the different cases of elevators because it's easy to mix it up and think, when accelerations are positive and negative for elevators. And it's a common type of problem, so I want to summarize it here. All right, so we're just going to complete this table of mass and weight for elevators moving at constant velocity, moving upwards and slowing, moving upwards and speeding up, moving upwards and slowing down, or downwards and slowing down, and moving downwards and speeding up. All right, those are our 5 cases. And I've already filled in the constant velocity case because we know that mass is just mass, and moving at constant velocity when there's no acceleration in the reference frame, weight is just mg. All right? But what about when there is an accelerating reference frame? Well, all right. Oh, I left off part D from the previous problem. Oh, excuse me. All right, so let's go. Let's run back to it real fast. So part D, by the way, of example 3, just asks, what happens if the elevator is in free fall? So the elevator is in free fall, then there's no normal force. You're weightless, okay? And you can show that by setting up the sum of forces and considering that A just equals G, and we can just even, kind of take a look right here, right? We had G minus A. Well, if A had the exact same value as G, it would just be 9.8 minus 9.8. Likewise for the person, it would be 9.8 minus 9.8, 9.8. And when that happens, then all the terms just zero out. So the scale would read 0, and the force on the hand by the strap would also be 0. Okay, the bag would appear weightless in the hand, and you would appear weightless relative to the floor. Okay, well, at least until you crash to the bottom, right? Okay, so now back to the concept question. So by the way, this is measured weight. I want to distinguish that from actual weight. So really, what should I have called this frame right here? I should have just called it normal force. Okay, but I didn't, and I think that's somewhat fair, or at least kind of a caution, a mistake on my part that is a word of caution. By accident. And that's because the terms weight and normal force do get used interchangeably, even though they probably shouldn't. And, case in point right here. Okay? But as long as we distinguish it as measured weight, hopefully that clears up any ambiguity. All right, so now let's finally look at that first case, moving upwards and slowing. All right, well, mass is just mass, doesn't change. Okay? And the weight would be m times g minus a, because as we saw in the previous example, or as we saw in example 3, you are lighter when the elevator is moving upwards and slowing. What about moving upwards and speeding up? Okay, well, that's where you're getting pushed into the floor because of your own inertia. And you can think of this in terms of Newton's first law too, because you want to continue, you as an object with mass, want to continue in motion at whatever state you're in. It would take an external force to change the state that you're in. So that means that if you're moving at a certain velocity upwards and the elevator then starts speeding up, you, having mass, the sluggishness of matter being possessed by you, resist that change. The manifestation of you resisting that change is you get pushed into the floor until you change along with the reference frame, which is the elevator. Okay? So in other words, you're heavier if the elevator is moving upwards and speeding up. All right, what about moving downwards and slowing? Also heavier. All right, because you want to continue moving down at a certain rate, the elevator is decreasing that rate, thus you get pushed into the floor. Okay, all right, that's one way of thinking about it. All right, what about moving downwards and speeding up? I bet you can guess later, because we already saw in the case where you're moving downwards and speeding up at a rate that is free fall, you're as light as you can be, you're weightless, right? Which was part D. All right, so that's a summary of kind of the different cases of, what is sometimes called effective weight. Okay, effective weight. All right, 2 final examples to wrap things up. All right, here are our tilted surfaces and how that affects normal force. So you stand on the bathroom scale in a cruise ship. Okay, the cruise ship is tilting to one side, but is not accelerating. Okay, you can combine these problems with acceleration, but for these examples, I did not. You notice that the scale reads a weight of 725 newtons, but you happen to know that your actual weight is 739. I don't know how you know exactly your weight, but you do, in newtons, no less. Assuming the scale is not broken, what must be the tilt angle of the ship? So let's draw a force diagram, a free body diagram. All right, so here is our person in our tilted ship. Probably not drawing the scale, right? I do a pretty dramatic tilt here. All right, you have to worry about tipping, right? That's a story for another day. Right here, you can't tip. All right, look at the forces. You got the gravitational force acting on the person. That's just mg. That never changes, right? But the normal force will change. Why? Because we can see here that the normal force is perpendicular to the surface. Gravitational force is not, You know what is perpendicular to the surface and anti-parallel to the normal force? A component of the gravitational force. So specifically a component that I call the y component. Why do I call it the y component? Because I've defined positive y as a direction that is normal. I'm essentially calling the y-axis the normal axis. So it's not pointing straight up on the page like you normally expect, right? You normally think like, oh, y and x, right? But it's just as often when you have a tilted situation like this that you define x and y like this instead. So that x is parallel to the surface and y is normal to the surface or perpendicular to the surface. Okay? Here though, x isn't relevant, so I left it off. Okay? So what does it look like then for net force? So from F net in the direction perpendicular to the floor, we have F net y equals Fn minus Fgy. And that's going to equal 0 because there's no acceleration of the floor. Okay? All right? And then that means that the normal force is just equal to Fg cosine theta. How do I know it's cosine? Because from geometry, I know that the tilt angle here is equal to this angle. Okay? Those two angles have to be equal to each other. All right? And so then we have, right, Fn equals Fg cosine theta. And the cosine, since I know, first of all, I know these angles equal to each other, and I know it's cosine from SOHCAHTOA, right? So just basic trig there. And then I want to isolate theta. So then I just divide both sides by Fg, and then take inverse cosine. So I'm just going to have inverse cosine of Fn over Fg, which actually ends up being just S725 over 739. The newtons would cancel out, so I purposely left off the units here. Okay? All right, so this cosine inverse of that ratio of numbers, 11.2 degrees. So actually it is quite a bit of tilt, but still not as dramatic as I drew. Okay? So there we have it. All right, how to find normal force for a tilted system. Okay? What about example 5? Well, example 5 is very, very similar. Okay, very similar. More simple than I usually have two examples. So maybe try this one before you look at my solution, right? So think of it as kind of extra practice. You can't turn it in, but think of it as extra practice, and then watch the solution if you can't figure it out. And because this is, I think, a good step to get a lot of practice with these, because it's so important to get used to free body diagrams. They show up so much in this class. So if a cup with a mass of 446 grams is placed on a waiter's serving tray, and in the process of maneuvering around a restaurant, the waiter tips the tray at an angle of 33.6 degrees, then what is the normal force exerted on the cup by the tray during the tilt? So the only difference here is that instead of solving for theta, we're just going to solve for Fn. Okay, so very similar picture, just place the person of water. We still have the normal force, we still have the same coordinate axis, right? Same geometry, same angles, same components of forces, same gravity. All right? So we care about F net in the perpendicular direction relative to the tray. Set up the same sum of forces. F net y is Fn minus Fgy, all right, equals 0 because the tray is not accelerating. All right, maybe I should have made it accelerating. That'd be more interesting. Right, then Fn just equals Fg cosine theta. Plug in our values here. We don't even have to isolate theta. It's just ready to go. Right, plug in our mass of our cup, plug in gravitational acceleration and cosine of 33.6, and we get that it weighs 3.8. And how much would the cup have weighed if the tray was level? Well, it would have weighed just mg, just this part. So it would have weighed about 4.5 grams. No, 4.5 newtons, excuse me. But it's lighter because it's tilted, all right? And that's going to matter when we talk about friction, because as you make things lighter, then now the friction force might not be great enough to oppose this component of gravity, the sliding component of gravity, or at least the component of gravity that can create sliding and acceleration in the parallel direction. But that's a story for the next lecture, all right? So thank you so much for watching this video and getting introduced to the ideas of weight, gravitational force, and the normal force.